In this video, we're going to be looking at part 4 of the Kinetics series, and we will be discussing reaction mechanisms. So to start this off, we need to first understand what a mechanism is. A mechanism is the sequence of events that describes the actual process by which reactants become products. And it's very similar to Hess's law, which Hess's law is something that you would have learned in Chemistry 1 during the thermodynamics chapter, thermochemistry specifically. So reactions may occur all at once or through several discrete steps. And so just like a proof, there's multiple steps that proves how a process is done. In this case here, we could have one reaction that describes it, or we could have multiple steps of reactions that goes through to solve for the overall equation. Each of these processes are known as the elementary steps, and you can call it elementary reaction, elementary process. I refer to it as an elementary step. So as we move on into talking about the specifics of these elementary steps, we have to understand what molecularity is. Molecularity is a process that tells you how many reactants are involved in the reaction for that specific step. So mechanisms are a little different than the experimental determined rate law, in that the rate laws themselves are actually determined from the equation, the balanced equation specifically. And so where we determined M and N using experimental data before, in mechanisms, you actually determine the orders based off the coefficients of the reactants. Now, there are different types of molecularities. There's unimolecular, bimolecular, and then termolecular. Uni just means that you have one reactant. Bi means you have two. And ter means you have three or more. In the case of the unimolecular, if we look at there at the first example, we write the rate law based off of it. So we have rate is equal to K times A to the first power, because only one A. Now, as soon as you add in another A, now we have bimolecular. So that also could be written as 2A yields the products. And so the 2, if you notice, is the exponent now. So be very careful, because when you're working with mechanisms utilize the coefficients. They're just proofs. You don't need experimental data to determine the exponents. However, if you want to determine what M and N are actually, you have to use experimental data. So now we look at the next few. We have the second bimolecular, which you have A times B. Well, I mean, you only have one A and one B. Look at the fourth one down. You see that there are three A's. Now this is a termolecular, and since there's three A's, we use the cubed root there for that. And this goes on to where you have two A's, so you have A squared and then a B, and then you have A, B, C. So again, the molecularity is just describing to you how many molecules are present in the reaction that are acting as reactants. So be careful whenever you write these rate laws, because as we progress in this PowerPoint slide, you're going to see that we use those balanced equations to write the rate laws and the mechanisms. So when we deal with mechanisms, there can be multiple steps, and some steps are slower than other steps. They're not all going to be happening with the same rates. We talked about that in the beginning. So what we need to do is figure out what the rate determining step is. Now, in order to do that, what we have to do is we have to figure out which one's the slow step. The slow step is typically going to be your rate determining step. Now, the slow step could be the first, or it could be the last, and we have to make sure we pay attention to where it is, because that is how we write the rate laws based off of the mechanism. So you gotta first understand where the slow steps are. Those will be given to you to begin with. All right, that's not going to be something you have to try to figure out on your own. That will be provided as information. So we look at this example here. This will be our first example that we study. The first says it's the slow initial step. So the reaction that we're going to have here, we're studying, is the NO2 reacting with CO. It forms NO plus CO2. So when we go into the lab and we go through the process and determine from the experimental data, the rate is determined to be K times NO2 squared. Now, if you look at the reaction, well, you say, if this is mechanisms, okay, why is it that we have NO2 squared, but if you look at the overall reaction above, there's only one NO2. All right, keep in mind the experimentally determined data, the rate law is determined from the data. So we actually have to come up with a mechanism. So now CO is necessary for the reaction, but it may not show up in this rate determining step, and that may be the reason why we see what we see. So this tells us that the reaction itself isn't just going to happen at once and one step, is going to happen in multiple steps. So a proposed mechanism for this would be you have NO2 plus NO2, so that'd be 2NO2 yields NO3 plus NO2. Now if you look above, I've already written out the rate law for the first step. Now I wrote the rate law for the first step. You could write the rate law for the second step, but it's not necessary because the first step is a slow step. So remember that slow step is the rate determining step. Now if you pay attention to the equation and what we saw that CO was not included in the overall rate law. Well, where is CO? CO is found in step 2, and step 2 is not the rate determining step. That's the reason why CO is not. It doesn't mean that CO is unimportant, it just means that it's not in the rate determining step. You can only go as fast as the car that's in front of you. So the other thing that we want to look at here are the intermediates, and so we kind of touched base on that in part 3. An intermediate is something that shows up and is quickly consumed. So it's a product that's quickly consumed as a reactant in the preceding step. So NO3 is produced in step 1, but if you notice in step 2, it's quickly consumed. It becomes a reactant. So that's typically the order that your intermediates are going to show up at. So if we look at where we have our initial step being the fast step, so something happened there. I don't know what happened there. Let me go back here. So these circles that you see here really should be here and here, and these are not necessarily based off of the overall rate law above. These coefficients, these exponents here, are actually coming from the mechanism, so we have to be careful here. So let's look at the mechanism. All right, with 2 steps, we have step 1, which is the fast step, and we have step 2, which is slow step. So what we're going to do is we are going to go through the mechanism, write the rate law based off this mechanism, and then compare it back to what we saw on the previous slide. So the first step, NO plus Br2 yields NOBr2. And then NOBr2 reacts with NO to produce NOBr. Now, if you pay attention to the first step, it's a fast step, so it's not the rate determining step. So we're going to be utilizing both steps here. So there's a little bit of algebra that we have to take consideration. So the other thing I want to do is make sure that you know that NOBr2 is considered the intermediate. So the first thing I do is I write the rate law with respect to step 1. Since this is an equilibrium, we're going to write the rate law for the forward reaction, and then we'll write the rate law for the reverse reaction. Now they are set equal to each other, so rate is equal to K1 times NO times Br2 is equal to K minus 1. Then minus 1 just means it's going in the reverse direction. So that's all that means. All right, now what we're going to do is we're going to write the rate law for the second step. All right, so next step, we understand that NOBr2 is your intermediate. Your intermediate should never end up in the overall rate law. So what we need to do is we need to get rid of it. We need to get it out of these rate laws. So what we're going to do is since we have NOBR2 here, we're going to get this equation. We're going to solve for this one, and then we're going to substitute that into the second step's rate law. So all we're going to do is divide by k minus 1. And what we see here is that the NOBR2 is equal to all this. So what we're going to do is we're going to take this and we're going to substitute it in here. All right, so we're going to substitute that into this part of the rate law for the second step. So in doing that, what we end up getting is all right. So this was what we had above that we substituted in. So we no longer have NOBR2 to be concerned with. So what we do now is simplify it. In doing that, we see this. Now, we're not going to solve the individual k's. What we can do is we can solve for the overall average, which is just k by itself. So that simplifies to that. Now, you also look at the fact that there are two NOs. So you have an NO here and an NO here. So that just becomes NO squared. And then we look at BR2. So the rate is equal to this. Now, if you go back and you look at what the rate was determined from the previous slide, you'll see that it matches that rate law. That's a good thing, because that means that our mechanism is a valid mechanism. When our rate law from the mechanism matches the observed rate law that we saw previously, that means that the mechanism is a valid mechanism and is usable. If it does not, then we're going to have to go back to the drawing board, and we're going to have to redo things and find a mechanism that will work and proves what we saw in the lab. So I'm going to go through here a couple of these. So the next few slides is just an explanation of what I just stated, and so nothing real different here. Just a different way of writing out compared to what I said. So, all right, there it is. Okay, so they get this result here. This result is same result of what we determined. So another example would be this problem here. And so we're going to work on this together here. So looking at letter A, it says write the rate law for the reaction based on the information. So it gives you some information. It says the following reaction observed to be first order with respect to O3 and NO2. So right now they're telling you that the rate, so they're giving you the orders. So you have O3 to the first power, and you have NO2 to the first power. So you got to be real careful, and you got to read. So you got to read the information they give you there. So now looking at part B, it says the following mechanisms have been proposed for the above reaction to determine the rate law predicted by each mechanism. So the first thing we're going to do is we're going to look at both mechanisms. We're going to figure out where the slow steps are. So the first mechanism, the slow step, is the second step. So this is going to be where we have to go through all the math and substitution. The mechanism 2, we see that the slow step is the first step. So we're going to write the rate law based off of that. So we're going to go ahead and do this one. So rate is equal to K times NO2 times O3. Because that's all you have to do there, because slow steps first. For mechanism 1, we got to go through that process. So I'm going to go ahead and just go through it. So pay attention and try to keep up. So here we have the intermediate being into a 4. So we're just going to do the same concepts before. We're going to divide out to k minus 1 and substitute that into for N2O4. We don't want that being a part of our overall reaction. So as we see, we're going to rearrange this to where we can get rid of the N2O4 because it's the intermediate. So we substitute all of this, which we would have divided by K minus 1 here. We substitute that in for the N2O4, so we end up with rate is equal to K2 times K minus, or K1 divided by K minus 1 times NO2, and we're going to go put that as squared because there's 2 of them there, times O3. Now we simplify this here, just this K, so rate is equal to K times NO2 squared times O3. Now what we are going to do now is we're going to look at letter A up here and say, okay, so that's the experimental rate law. Which of these mechanisms matches the experimental rate law? So we look at mechanism 1. We see right off the bat that we have only one NO2 in the experimental, but here there's 2, so that one's not going to work. We look at mechanism 2, we see that we have 1 of each, so that matches up with that. So mechanism 2 would be the mechanism that would be the appropriate to use for explaining the experimental rate law. So that's how mechanisms work. So mechanisms are utilized to sort of explain, why we see the experimental rate laws, and we also are able to determine the intermediates too. So last thing we're going to cover in this are catalysts. So catalysts, again, are species that will cause the reaction to go faster by altering the mechanism that you normally would observe, and they do this by decreasing the activation energy. So obviously if you lower the hill, it's going to be much easier to get over, so they do this by altering the mechanisms. So you can, the graph you see here, the blue line represents a catalyzed reaction and the red line represents the uncatalyzed. So what you see is a change in the size of the hill. So the activation energy for the catalyzed mechanism is much smaller than the size of the hill for the activation energy for the uncatalyzed reaction. So catalysts come in a couple of different forms. So there's 2 different types of catalysts. There's homogeneous and there's heterogeneous. Homogeneous means that the catalyst is and all the stuff that's around it that's reacting are the same physical state. So a good example is your body. Your body is all aqueous solution, and the catalyst, enzymes in this case, are aqueous. They're all dissolved into water. A good example of a heterogeneous catalyst would be your car. It has a catalytic converter on it. The catalytic converter is composed of metal, in this case platinum, and your car, as it ignites, the combustion chamber releases gases, so the gases travel through the catalytic converter and get converted into good gases. So that's an example of a heterogeneous catalyst. And both work similar, but obviously the more homogeneous it is, the more quicker it's going to work. So, but they both are very quick processes. So, like I said, enzymes are basically the catalyst in your biological system. You probably remember that the lock and key mechanism from biology, where the substrate fits in, and the reason for that enzyme there is it forces the molecules to be positioned in the correct orientation. If it didn't do that, there may never be a chance for them to find each other. So that's the importance of that lock and key mechanism, and that alone is what reduces the amount of energy it takes for the different reactions to take place in your body. So that's all we have for part 4. This concludes our series for videos for kinetics. Thanks for watching.